Okay, guys, I kept saying that I will be uploading university level physics topics, and I kept postponing because it's really hard for me to figure out a way to present this material because I'm used to teaching it in a class where you have an interaction with your students, you get questions, you get to think about it, etc. So it's a little bit hard. So I decided to start with an experiment, pretty much an experimental class, and see how it goes. And it's related to the class of classical mechanics. So I'm gonna write it up top. So this kind of material, I started with a typo, I'm sorry. So this type of material would appear in a class of classical mechanics for majors, assuming that you guys are in the US, but even in Europe, this is classical mechanics that students take if they study physics or something close to that, maybe applied physics. I'm not really sure if in applied physics curricula they have classical mechanics, but this is the mechanics you take once you do some introductory physics. Okay, so you need to have some solid understanding of introductory physics 1 and 2. Introductory physics 1 is usually, again, classical mechanics, but at the lower level. And then introductory physics 2 is usually electromagnetism, again, at the lower level. So anyway, let's get to this. So from classical mechanics, I will be teaching using the book of Marion and Thornton, which is a popular book used in the United States. I'm actually checking right now. So I have the 4th edition. I'm pretty sure it's old because it's been a while since I studied. So I have the 4th edition. But I think there is a 5th edition. I'm pretty sure there is a 5th edition. I'm not sure if there is a 6th edition. Anyway, and from just to get started, I'm not gonna start from the beginning as usual. I'm just gonna present you something I like as a topic, and I will get the reactions from you and then kept going with this. So I'm gonna discuss what is known the Brachistochrone problem. Okay, this is a Greek word, and I'm an actual Greek, which makes it harder sometimes because I don't know how to pronounce things in English. So in Greek, brachis means fast, chronos means time. So the Brachistochrone problem means finding the fastest path in a gravity field. Okay, so in Marion and Thornton, this is a topic discussed in chapter 6. I'm gonna write it here. So chapter 6 in Marion. Okay, Marion is with 1R. Okay, so chapter 6 in Marion, and this type of topic is usually under the chapter under a chapter called calculus of variations. Okay, this took longer than I anticipated, but okay, I mean, I just wanted you to have a general idea of what I will be discussing in this video, in this particular video, because hopefully eventually I'm gonna have the whole class uploaded. But so for now, we will just talk about one problem. Okay, it's like an example problem. The calculus of variations is also taught to mathematicians, by the way, but I'm a physicist, so I'm gonna be doing things from the perspective of a physicist. Okay, so let's start with a clean page. So the task is to calculate the fastest path in terms of time. Fastest in terms of time. For a particle, moving from a point x1, y1 to a point x2, y2, which is lower in terms of the y1 coordinates, so at the lower height. Okay, so if you draw this thing, it's going to look like this. So if this is your x-axis and this is your y-axis, then let's use a different color. Then if you start from a point x1, y1, the particle needs to end up at the point x2, y2, and the task is to find the fastest path. So is it a straight line? Like if it goes on a straight line, assuming that, imagine, the best way to imagine this is maybe imagining a ball sliding through some surface. Okay, this is going to be a one-dimensional surface, but maybe a line. Okay, like a ball going down a line. So is the straight path the fastest? Maybe a parabolic path, maybe a circular path like that, maybe something else. I don't know. We will find out. Okay. The first thing I want you to notice is that that the path, which we mentioned here, is a function y equals y of x. Okay, so the path is a line. It's we're trying to find the equation of a line, pretty much. Okay, the equation of a line along which a particle will travel the fastest between the points between the point x1, y1 and x2, y2. Okay, the point with coordinates x1, y1 and x2, y2. Maybe it's better to say p1 and p2. Okay. Now, one point of confusion in the calculus of variations is that people usually automatically go to the Euler equation, which looks like this. I'm gonna write anyways, theta f. So partial of f with respect to x, I believe. No, with respect to y, I'm sorry. Minus d over dx of the partial with respect to y prime is 0. Okay, so this is the Euler equation. So if you go here and try to guess the functional or try to come up with a way to find the functional, etc., you're going to get confused and it's really hard. So that's not the way to go, actually, when you work with calculus of variations. So some general notes. So in the calculus of variations problems, in calculus of variations problems, we always optimize meaning that we find the minimum or maximum, a quantity, actually a physical quantity is better. Okay, so a physical quantity, and this physical quantity is most of the times a length or maybe time, like in our case, maybe energy, surface area, etc. Okay, so we need to optimize, like find the minimum or maximum time needed to traverse a path, energy needed to traverse a path, and so on. Okay, so the starting point should not be, and maybe I should write there. So your starting point, since someone is watching this, hopefully, so your starting point should not be the Euler equation. but an integral. Okay. And actually, the Euler equation is derived from an integral. Okay. And we will see this integral in a minute. Once you find that integral, okay, once you write the integral down, comma, then try to write the integrand as a function of y prime, and maybe x. Okay. So to remind you, if I have an integral I equals to, I don't know, let's say it's an indefinite integral of some function f of x dx, this right here, this is the integrand. Okay. Now, these are some general remarks, and let's go back to the problem now. Okay, I'm sorry, I keep talking about it without doing anything about the problem. So let's see. I'm redrawing the situation. Okay, so we start from some point x1, y1, and we are going to some point x2, y2, and let's say that we have this crazy path like that. Okay. Now, okay, we need to write down an integral. Okay, so the particle going from point 1, so p1 to p2, if we have a particle going traveling between these 2 points, it will take a time dt to travel, right? And this dt is going to be given by ds over the velocity, right? How did I come up with that? Because simply the velocity is equal to ds over dt. Okay, so this is the first step. What is this ds? It's an infinitesimal part, maybe. It's an infinitesimal piece, it's better. Okay, it's an infinitesimal piece of this path. Okay, and the path is the blue line. Okay, ds is one very, very small, infinitesimally small part of this path. Okay, and because it's infinitesimal, we can think about it as a straight line. Okay, and if we zoom in, we will see that vertically, if the particle goes from this point to this point with red marker, then vertically it's going to travel by dy and horizontally by dx. Okay, and at this random location over here, okay, its velocity is going to be v. How can we calculate v? With conservation of energy, pretty much, right? Because up here the particle only has potential energy mgy, and it has a kinetic energy 1/2 mv squared down there. So let's write the energy equation. Mgy is 1/2 mv squared. So v is simply the square root of 2gy, and then ds squared is the square root of dx squared plus dy squared. So okay, we're making some progress. We still haven't written down an integral, so let's do that. So we need to optimize the time dt. This dt is going to be the integral from point x1 y1 to point x2 y2 of ds over v, and we just found that ds is the square root of dx squared plus dy squared over the velocity, which is the square root of 2gy, and this whole thing is inside an integral, x1, y1, and x2, y2. Okay, now recall what I told you here. Once you write down the integral, try to write the integrand as a function of y, y prime, and maybe x. Okay, so how can we do that? It's already expressed in terms of y there, right? But we need to uncover a derivative with respect to x. How can we do that? We simply, sorry, I didn't mean to do that, but let's keep writing. First of all, we can take the 1 over the square root of 2g outside the integral because it's a constant, so it doesn't do anything for us. And then we can write this as dx squared times 1 minus dy over dx. I ran out of space. I'm sorry. Let me rewrite this. As I said, this is new for me, so I'm learning how to present material on an iPad, so it's kind of hard. So we go from point 1 to point 2, and it is implied that P1 is x1 has coordinates x1, y1, and P2 has coordinates x2, y2. So I take dx squared outside, and then I have the square root of, actually, I confused myself again. Okay, one more time. So dx squared 1 plus dy over dx squared. Okay, and this whole thing should be under a square root, and then we have the square root of y, and then we can take this constant out. Okay, let me move to a clean page. So this simply becomes 1 over the square root of 2g times the integral from x1 to x2, since you got rid of y. Actually, no. Yes. So we have a dx and then a square root. As I said, it's hard to present this material on an iPad. So this dy over dx is simply y prime, right? So we have 1 plus y prime squared over y. Now, what is that? That's our functional, as they call it, and it's the integrand expressed in terms of y, y prime, and maybe x. In this case, it's actually not expressed in terms of x, which is a key for this problem, and I'm gonna talk about that in a moment. But we found our functional, and functionals in the calculus of variations are written as f, lowercase f, y, y prime, and then semicolon x. And this means, it's written like this because this means that the functional is a function of y, and y is a function of x. We know that, but when we work with a functional, we treat y and y prime as variables, okay? And you will see what I mean in a minute. So our functional is simply 1 plus y prime squared over y, okay? So let's call this equation 1. So to summarize, remember what I told you, in the calculus of variations, you find the functional by writing down an integral, and our integral is this one, okay? Because we need to minimize the time. We need to minimize the time, this guy, and dt is expressed as ds over v. And in writing down the algebra, we ended up with a function, okay? And now is the time to use the Euler equation. But notice that the partial derivative with respect to x is 0, okay? Remember I told you that when we work with functionals, we consider y and y prime to be variables, okay? We know that y is a function of x, but when we take the partial with respect to x, we don't try to do partial derivatives of y with respect to x and stuff like that. No, we treat y and y prime as variables of their own, okay? So the partial derivative of this functional with respect to x is simply 0 because there is no explicit dependence on x. And what I mean is that if there was an x down here, then okay, this partial would not be 0, but there is no x inside our functional, so it's independent of x, so the partial is, with respect to x, is 0. The Euler equation comes in two forms. So Euler equation, the first form is the one I wrote down a few moments ago, which is the partial with respect to y minus d over dx, partial with respect to y prime, and this is 0, okay? Let me squeeze this over there, okay. Okay, now it looks prettier. The second form, there is a second form, so which is equivalent, okay? Second form is partial with respect to x minus d over dx of f minus y prime partial with respect to y prime equals to 0. These two expressions are the same, but this expression is useful to us because notice that in our case, this partial is 0, okay? Which means that the first derivative with respect to x of this guy over here is 0, which means that that guy is 0, is constant, right? So that's a key for our problem. And let's write down, okay, equation 1 is our functional. Let's write down that f minus y prime partial with respect to y prime is c, which is some constant. This is our equation 2, and I'm going to write here that partial with respect to x is 0, therefore this applies, okay? And now let's go find the partial. So we need the partial of our functional with respect to y prime. So we need to do 1 over the square root of y. This is our functional, right? And then since we have, again, we treat this y prime as a variable, okay? Think about it as x, okay? It's like having the derivative with respect to x of the square root of 1 plus x squared, okay? So it works the same way. So this becomes 1 over 2 times the square root of 1 plus y prime squared, and then times 2 y prime, because again y prime is just a variable in this case. So the partial with respect to y prime is simply y prime over the square root of y1 plus y prime squared, and let's call this equation 3. Now let's plug everything into, let's pull everything together. So from equations 1, 2, and 3, we will pretty much plug equation 3 and equation 1 into equation 2, okay? So we get that the square root of 1 plus y prime squared over y minus y prime squared over the square root of y times 1 plus y prime squared is c, okay? And I am really tempted to just stop the video and then give you the final answer, but as my chair at a college where I worked used to say, nobody under the age of 21, I think, he used to say that, knows how to do algebra. So I'm not under the age of 21, so I claim that I know how to do algebra, so I will keep going. So what I will do is that I will multiply both sides of the equation with this guy, okay? So on the left hand side we will have the square root of y times 1 plus y prime squared times this expression over here, 1 plus y prime squared over y. And then since we will multiply the denominator with the numerator, does that make sense? Anyway, since we are multiplying with this expression, the second factor will be just y prime squared. And this should be equal to c times y times 1 plus y prime squared. Okay, we have some nice simplification here. Notice that we can cancel this, provided that y is not 0, of course, which is not. Okay, and then we have 1 plus y prime squared multiplied with itself under square root, which means that the square root is gone. So then we get 1 plus y prime squared, then minus y prime squared. Remember, this is the left hand side, and the right hand side is the one we just had, so it's the same, nothing changed. Y times 1 plus y prime squared. Okay, this cancels, and we get 1 is equal to, and I'm gonna take the square of both sides now, so 1 is equal to c squared y times 1 plus y prime squared, and we reach the point where we get this equation, 1 plus y prime squared is equal to 1 over c squared y, and then I'm gonna rename this part. Since this is a constant, I'm gonna rename it to k squared, okay? Which is like doing nothing pretty much. So 1 plus y prime squared is k squared over y, okay? And then we get, we can solve this for y prime. So y prime is the square root of k squared y minus 1, which I can write as y minus y. And then we can write this as dy over dx is equal to the square root of k squared minus y over y. Therefore, dx, and you will see why I did that. It's a little bit like cheating because I know what we're trying to find, which is the trajectory pretty much, the equation of y, the equation of the path. So dx is equal to the square root of y over the square root of k squared minus y times dy, okay? We will call this equation 4, okay? This is sometimes called the first integral, I think, in the calculus of variations. Don't quote me on that, but let's move on. Now set y equal to k squared over 2 times 1 minus cosine theta, which is equivalent to writing k squared sine squared theta over 2. Okay, this k squared is the same as the k squared that appears in our differential equation, okay? All right, let's call this equation 5 and plug this equation back to 4. So dx can be written, so from 4 and 5, we can write that dx is simply k, the square root of y is k sine theta over 2, and then dy stays there. And then in the denominator, we have k squared minus k squared sine squared theta over 2. So k is a common factor. And then we have the square root of 1 minus sine squared theta over 2, which is cos squared theta over 2. So we end up with cosine of theta over 2, and this k cancels. So this looks pretty, and we can take one step further and divide dx with d theta, which reveals on the right hand side this expression dy over d theta. And this is something we can calculate because we do have an expression of y with respect to theta, okay? So dy over d theta is simply, what is it? If we use 1 minus cosine theta, we find k squared over 2 times sine theta. Okay, and this is equation 6. Now, from 5 and, this equation 6, let's name this equation 7. See, algebra gets confused, guys. So anyway, from equations 6 and 7, we find that dx over d theta is k squared over 2 times sine theta over 2 over cosine theta over 2 times 2 sine theta over 2 cosine theta over 2. This might be confusing, but remember this expression here is on the numerator, so this cosine theta over 2 cancels with this one, and then these 2 cancels with these 2, and we are left with dx over d theta equal to k squared sine squared theta over 2. And this is something we can integrate, guys. So dx is equal to k squared and then sine squared theta over 2 times d theta. And we can integrate dx from 0 to x. And to do that, we need to turn x into a prime. So we are integrating with, into a dummy, sorry. So we are integrating with respect to dx prime, where prime is not a derivative here, it's just a dummy variable. And then we integrate this from 0 to theta, so we have to turn this theta into a dummy by taking the prime there, which is not a derivative again. And I fed this into Mathematica. Okay, I'm not gonna go over how to solve this integral, so I'm gonna give you the final expression. X is k squared over 2 times theta minus sine theta, and together with y equals to k squared over 2 times 1 minus cosine theta. These two equations over here give you the cycloid. These are the parametric, so these are the parametric equations of a cycloid. I don't want to plot this. There are many videos on YouTube, and you can Google it and find what the cycloid looks like. But this is the style I want to go with when I present these lessons online. Let me know what you think, if this is helpful or not. And I hope to come back with more videos. This is a difficult time in my life because I'm looking for work and I try to find things to do. So this is something I like to do. So I hope this is useful to someone. I guess like and subscribe and so on, and see you in the next one. Bye.